Good morning, everyone. Welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing. This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities. And every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by the headliner giving us a keynote presentation.
Today, we are thrilled to have Sarah Kushner as our opener to talk about levitating objects. I hope I have that right. And Dr. Mélina Skouras as our headliner to talk about inflatable shapes. If you have any questions for the speakers, feel free to write them either in the YouTube live chat or on our Discord channel. We'll be monitoring both. Our first speaker today is our very own Sarah Kushner. She is a PhD student in computer graphics at the University of Toronto, working on constructing 3D scenes for animation using 3D printing. Her work of fabrication is truly breathtaking. In my experience, if you're ever in our lab and you're bored or frustrated with your own research, you can always just go and see what it is that Sarah is doing, and it will almost certainly will be something super cool. I miss it a lot, as you can probably tell. Let's all welcome our lab's resident levitation wizard, Sarah Kushner.
Hello, everyone. Can you see me?
Yes.
Okay. I will share my screen. Okay. Can you see it?
Yeah, that works.
Okay, great. Thank you for the introduction, Sylvia. Like she said, I'm going to be talking about my most recent work with Risa Ulinsky, David Levine, Karen Singh, and Alec Jacobson. And it's going to be about levitating rigid objects with hidden rods and wires. The goal of this paper is exactly what it sounds like, given a set of rigid objects, some supporting surface, and a viewpoint distribution. How can we generate a support structure that holds these objects in place but is also invisible to the viewpoints? This problem can be seen in a lot of places. Like in this example, a statue is being held up by rods, which are attached to the building behind it. In this example from the set of the movie 2001, A Space Odyssey, this actor is suspended by wires so that from the camera they're invisible and he looks like he's floating. And in this 3D zoetrope, where each small bird is held up by its own rod. And finally, in this example from a museum, this whale skeleton is floating, and experts are actually paid a lot to come up with hidden rods and wires that support this invisibly, but also so that it's sturdy enough to be safe hanging in a museum. So you might be thinking, why not just place them manually in the spots that look invisible? Well, as you increase the complexity of the scene by adding many small parts, a more complicated support surface, and multiple viewpoint distributions, this problem becomes way harder. So the first goal is we want to hold rigid objects in their place under a force. So the question becomes, what do we put between the object and the support surface? To start working on this goal, we first sample points on the surface of every object in the scene, and we create what is called the ground structure. This is a complete bipartite graph between all the points, and we're going to be extracting edges from this graph, which will become rods in the resulting truss. And we take an extra step that most of these methods don't do by pruning the graph because we want to get rid of edges that we know we definitely don't want in the result. So for example, we do some simple ray shooting to get rid of edges that intersect the bunny. We don't want edges to go through our objects. And so unsurprisingly, this having fewer edges speeds up our final optimization quite a bit. So we want to extract the set of supporting rods. To do this, we minimize the total volume of the resulting truss, which is the sum of all the known edge lengths times the unknown cross-sectional areas which we are solving for. We minimize this subject to some force and torque balance constraints. For a solution to be physically valid, it must be in static equilibrium. And this just means that the total force on the object must be equal and opposite to the applied force, and we want the internal torque for each object to be equal to 0. Because we are minimizing the volume as opposed to the squared volume, we can guarantee we get the sparse set of supporting rods because most rod areas go exactly to 0. Here you can see a plot of the sum of areas, and the solution is where our linear constraints meet these isolines. And in this one, they land on a corner, which means that the value of A1 is exactly 0. This is opposed to the sum of squared areas where our linear constraint intersects at a point where both A1 and A2 are non-zero. In addition to these static equilibrium constraints, we also don't want the rods to break. So each rod is given a maximum yield stress based on which material it's going to be made out of in fabrication. And this just means how much force a rod can take before it breaks. So we want this force to be less than or equal to the maximum. In the axial direction of the rod, we want it to be resistant to compression, which says how much can you push on the rod before it breaks, and tension, which says how much you can pull on the rod before it breaks. And unlike the traditional ground structure methods, we also have rods that are resistant in the normal direction to the rod. So we want our rods to also be resistant to bending. So for this, we add a linearized shearing force that acts counter to this. And we find that adding this shearing force actually helps a lot in making the solution more invisible. So as you can see on the left, this is without the shearing term. And then on the right, you can see that it's a lot less visible. So our first goal is completed. The bunny holds up underneath a force, but from the expected viewpoint, the rods are very visible. So we need to address our second goal, which is to hide the supporting rods from the viewpoints. So we want our solution to look more like this. So right now we are minimizing the volume, and we modeled the static equilibrium equations as hard constraints, which means the solution must be physically valid. We would want the solution to also be completely hidden, but if we model this also as a hard constraint, we might end up in a solution or in a situation where there is no solution. So we have to add our visibility term to the objective. We just want it to be as hidden as possible. So in order to do this, we need to penalize edges that are very visible to the viewpoint distribution. So to do this, we're going to give each rod a scalar visibility value. And because we can't see the entire surface area of a rod from a viewpoint, we see only the part that's facing us. We want to compute the visible area of a rod. And this is just the length of the rod times the thickness of the rod. But this is not always what we see. Because due to foreshortening effects, we actually see even less of the rod. So what we want to compute is the projected visible area. This is a function of the angle between the vectors that go from the viewpoint to either end of the rod. This fits our intuition because if we look at a rod straight on like this, we can barely see it. And we integrate over the rod by uniformly sampling points and shooting rays from the viewpoint. But this does not account for occlusions. So in this example, say we're trying to compute the visibility of this rod in the scene with the bunny. We can see that actually some of the rod is invisible because the bunny is blocking it. So when we shoot rays at the rod, we count all of these hits if it intersects the bunny before it gets to the rod. So we sum up all these hits and then we weight it by the angle that we talked about before. So now the projected visible area of the rod also depends on occlusion, so which part of the rod is actually visible. And then, of course, to get the entire visibility score for a rod, we need to integrate again up over the viewpoint distribution. So on the left, you can see the pruned ground structure has edges now colored by their visibility. So we can add this term to our objective, but because our term is because it's in terms of the rod thickness, we actually have to square it so that it is also in terms of the cross-sectional areas. This final formulation is a linear program, and this can be solved using standard solvers. So our formulation works. We get a solution which is mostly invisible but physically valid, and the result of this is that I printed it and it holds up exactly like we would expect. We also include assembled examples. So in contrast to just 3D printing it, we also have examples that I assembled myself. So in this example, we want the ghost to be held up and look like it's floating. So I use wooden dowels, and as you can see from the video, from the expected viewpoint distribution, we can't see them. And from our more complicated example from the beginning, we can see that our solution is invisible from both viewpoint distributions. Our system also can give solutions which contain wires, which can be thought of as rods that only have tension forces. So here you can see a seagull is being held up by fishing wire. And we support solutions that have both wires and rods. So in this example, a giant balloon is hanging outside of a museum. And from the expected viewpoint, you can't see the support. So it looks like it's floating. This is important because sometimes an invisible solution isn't possible using only rods. So it's important that we also have wires. And I also assembled an example that has both wires and rods, and I wanted to make it look like these little sheep are floating and jumping over the fence. And my most favorite example is this 3D zoetrope. So we applied our algorithm to each of the 16 frames in this animation, so that from the front, it looks like this backflipping cartoon is floating. So as you might have noticed, the solutions we give are good in that the rods are invisible from the viewpoint. However, the shadows of the rods are not guaranteed to be invisible. So like you can see here, unfortunately, you can still see the shadows. There are other visual cues we don't account for, like reflections and transparent objects. And this would be fun future work, which might be solved using multiple ray bouncing when we compute our visibility term. Also, rods or edges selected from the graph, when they become thickened rods, they might intersect with each other. This is a problem common to all ground structure methods, and surprisingly, in practice, I hadn't found that to be a problem during fabrication. Our algorithm also assumes as input that the scenes are well crafted, but this design process is non-trivial, and it would be cool to have an interactive tool which could give users hints on where to better place objects so that they would be supported. And right now, our wires and rods are treated completely separately, as would any different material we choose. But with the rise of multi-material printing and metamaterials, it would be interesting to have a more continuous representation between different materials. Thank you for listening.
Thank you very much, Sarah. You can stop sharing screen now. That was a really uplifting presentation, may I say. We will now move on to our headliners talk, and we'll have remember a joint Q&A for both of them, so you can leave your questions for Sarah in the YouTube live chat or on our Discord now, and we'll ask her at the end. Our headliner, Dr. Mélina Skouras, is a researcher at Imagine in Grenoble in France. Before that, she was a postdoctoral researcher at MIT, and she obtained her PhD from ETH Zurich in Switzerland. In a way, her work takes the opposite view from our previous speaker. If Sarah tried to make rigid objects stay in place and avoid the effects of ambiental forces like gravity and others, Dr. Skouras designs materials which use these forces, like gravity, to precisely take their shape. The videos of her work that you can find on her website are really, really cool. I'm very glad that she's the speaker that will be closing this colloquium season. So let's all give a very warm welcome to Dr. Mélina Skouras.
Thank you very much for the introduction. So hi, everyone, and thanks also for the invitation. So let me start by sharing my presentation. Share screen. Okay, so in this talk, I will talk about the design of inflatable structures. So when I say inflatable, I'm actually referring to this type of objects. So these are structures made of flat panels, which are made of a quasi-inextensible material. So the panels are sewn or sealed to each other to form closed surfaces. So like this. So if you want to design such structure from having a 3D given target shape, what you need to do is to decompose this 3D shape into different pieces that will correspond to a panel. And this is particularly challenging because when you have pressure forces, these panels will deform. So you need to infer what will be the effect of the physics on the panels, what the deformation will be, and you need to mentally reverse this process. So what we propose are tools based on computation that will actually do that for you and help you in the design. So these tools usually rely on an internal component that will simulate the structure. So that's to say that they will predict or give you the 3D shape that correspond to a 2D set of 2D panels. And this is actually already a difficult problem. So let's start by this one first. So how do you simulate such a structure? So typically what you do is that you rely on continuum mechanics and discretized equations of equilibrium. So you can map each point X in the reference configuration to point X in the deformed configuration. And from this, you can quantify the local deformation of the objects by looking at the deformation gradient F. And you can construct the right Cauchy-Green tensor C, which is FTF. So typically the deformation, so the energy density of the material depends only on the current state of the deformation, that is C. So you can define it as a function of C. So now when you apply external forces, such as pressure forces, this will create a variation in the internal energy, and equilibrium will be reached when these internal forces balance the external forces, so the pressure forces here. And these equations, which is nonlinear, can be solved using standard finite element method, for example, using linear base functions. The problem in practice is that for inflatables, you have wrinkles that appear at the seams location that are tricky to handle. So to understand this issue, let's look at a simpler example. In this case, an airbag shape made of two discs like this one. So this is the top view and this is the side view. And when you apply pressure forces inside the structure, the center of the two discs will move apart. And if the discs are made of an inextensible material, this means that any radial line, like the one which is in orange here, will keep its original length. So this means that if the height of the balloon increases, its circumference much decrease, which means that you can that you actually get compression on the seams. And since the material usually have a much more resistance to bending than stretching or compression, you will have buckling in this area. And it is well known that buckling is tricky to handle numerically. So this is because these wrinkles can actually form inward or outward. You have also this phase invariance when you rotate the wrinkles. So this translates into singular values in the Hn of the energy of the system. In addition to that, you need to use very high resolution meshes to be able to resolve the wrinkle geometry and to correctly predict the global shape. So what we do to avoid this problem is that we turned toward tension field theory to convexify the energy of the system. So instead of having an energy density that schematically look like this, where you have this increase for compression, so this is the red area of the plot here, we will modify it to have something like this. So now it's 0 when you have compression. And if you do that and simulate your structure, you will end up with something like this. So you won't have any more wrinkles. You'll have compressed elements instead in the locations where you have these wrinkles. But the global shape of the object will be captured correctly, which is great. So if you like formulas, this is what they look like in our case. So here we used neo-Hookean material for which the energy density can be parameterized as a function of the two eigenvalues of the C tensor, the right Cauchy-Green tensor that I mentioned before. And this is what the convexified energy density look like. So when we have, when the two singular values are smaller than 1, this means that you have compression in the two principal directions. Then we set the energy to 0. When you have tension in one direction and compression in the orthogonal one, this means that you have well-defined wrinkles. Then we set the energy to the minimum value of the original energy when you fix the positive eigenvalue and change the other one. And when you have tension in both directions, then we use the original energy density. So here are some results. So this is the ground truth that we computed using a mesh which has about, I think, 60K elements using the original density model. And this is what we get with our relaxed formulation. With meshes using having increasing resolutions, and you see that the global shape of the object is almost the same in the 3 cases, and you can also see that the locations of wrinkles that is indicated by compression of the triangles shown in red here is also good for the 3 resolution, the meshes of the 3 resolution. So that's nice. So even if we don't get the geometry of the wrinkles, we can say where they're going to appear, the red triangles here. The global shape is well captured, even with coarse simulation meshes, which is great. So we can actually use coarser meshes than before. So we win on 2 sides. Not only the simulation, so the system is easier to solve, the numerical problem because it's more convex, but we can also decrease the number of degrees of freedom that we need. So we use this simulator, and this is comparison. So these are error plots between the mesh on the left and the mesh the meshes on the right that show you that the error is really localized at the wrinkles locations. So this is for the simulation. So we can go from 2D to 3D, but actually we are interested in the opposite. So we want, we assume that we have segmented target mesh and we want to compute the optimal panels. So the optimal shape for the panels that will constitute this inflatable. So the problem, the minimization problem that we want to solve can be casted as follows. So we want to optimize for the rest shape of the panels, X bar. such that the distance between the inflated mesh X and our target mesh X target is minimized. And we use a matching energy that captures both the distance between the surfaces of the two meshes and measures the deviation of the seams locations from the initial seam curves. We also have some terms that captures some fabrication requirements. In particular, we want adjacent panels to have seams of same length. And we also want to privilege smoother boundaries for the seams. And of course, if we want to fabricate these structures, they should correspond to the feasible solution. So it means that they need to correspond to a static equilibrium shape for the system. So here, this means that the membrane forces should balance the pressure forces. And this can be solved, for example, using sequential quadratic programming. And in practice, we also added a remeshing procedure when the aspect ratio of the elements was really bad. So this is what we get for this simple sphere example. So we started with 3 panels. So you get initially this kind of elongated shape that looks like a bit like a rugby balloon. And this is what you get when you optimize the panel. So we get something, so the panels really change their shape. They are much more elongated. And the result actually looks a bit like, or reminds a bit of the tennis ball. Except that in this case, we have 3 panels. And the result is also much spherical. So we reached our goal. And you see that remeshing is really necessary. Otherwise, you would really have crappy meshes. So we incorporated this optimizer into a design tool. So because the seams have actually an impact on the aesthetics of the structure, we allow we let the user draw them directly on the target mesh. So the user can import a mesh, draw seams on top of this mesh. So this is actually a task which is cool to do. And then when they are ready, they launch the optimization of the panel. So on the left window, the top left window, you see the inflated shape. And on the bottom, you see the flat panels. So we start the we initialize the shape with some standard flattening algorithm, and then we optimize the panel shapes. And if you don't like the result, you can actually adjust, change the layout, add more seams, remove seams, or edit them, and the algorithm will restart. So here I stopped the video a bit early so you don't actually get the optimal result for this shape. We also add a feature to be able to add or specify internal panels. So these are useful when you have concave features, for example, in the internal part of the ears of this fox head, or to have sharper creases like around the nozzle of the fox. And these panels are optimized in the same way as the others. Here are some results that we fabricated. So the sphere example, the teddy bear, and the fox. And here are some additional results that we computed in simulation. So these are the target shapes, and these are the results that we obtained. So some of these models actually contained internal panels, which are here. And their results look nice overall. So you can see that some shapes are more difficult to obtain than others. For example, this twisted beam that have a lot of sharp edges. Okay. So I showed you so far how to design inflatable structures that are filled with air, but we can actually design panel-based structures that will be filled with other materials like plaster or concrete. So in this project, which is a collaboration with Emily Whiting's group and Charlie Wang's group, what we wanted to do is to use these fabric panels to create molds forecasting. And this is a very appealing fabrication technique because it doesn't require specific hardware like 3D printers. The material that you use is very cheap. So that's fabric, plaster, some standard material for the hanging structure. The mold is very easy to transport. It's very light. And you can also easily create large-scale structures. And also unmolding is easy because you can easily cut the fabric panels. So this fabrication technique has been investigated a little bit in the architecture community and by artists. So you have two examples here. But as is often the case, this is typically an experimental process based on trial and error. So what we wanted to do with this project is to systemize a bit the process and propose a design tool to automate the design of these panels. And to enlarge the shape of the space of the shapes that we could obtain, we also allowed ourselves to use external supports. So we use 3 types of external supports. So strings that connect some points on the surface of the fabric to the hanging supports. So these strings are useful when you have arches. We also use the cables for obtaining sharp edges or concave edges. So these cables plays a similar role as the internal panels that I mentioned before, except that when you use plaster, for example, you cannot use internal panels because they will restrain the flow of the fill material. So yes. And the last kind of external support that we've used are planes. So this is to get planar support surfaces that are difficult to obtain with pressurized system because the shape tends to bulge out. So this is a minimization problem that we solve here. So it looks pretty similar to the previous one. So we still want to optimize for the rest shape of the panels, X bar, such that the shape of the formwork when plaster is poured in is as close as possible to our target shape. And we also have our fabrication constraints related to the smoothness of the seams and the fact that they need to have the same length for adjacent panels. And of course, we still have our fabrication physics constraints that say that membrane forces plus pressure forces plus the forces applied by the external supports on the fabric must sum up to 0. But one important difference here is that when you use plaster, gravity plays a much more important role. In particular, the pressure value is not the same everywhere on the surface of the object and depends on the height of the application point of the force with respect to the surface of the liquid. So it varies, it scales linearly with the height. So here the XD in the formula represents a 0 pressure reference point on the surface. And this means in particular that the orientation, the hanging orientation of the structure matters. And that will have an impact on the results because if you change the orientation, the pressure forces will be different. So to illustrate this effect, we can look at this example, which has a S shape. So this is what we get when we hang it using different orientations. So the first one here corresponds to the blue direction here. The second structure corresponds to the orange, the red orientation. And you see that all these shapes are very different. So this means that we actually ended up in different local minima. And this is not surprising because the problem we are trying to solve is very non-convex, non-linear. So what we do to try to reach a global minimum is to draw inspiration from the algorithm proposed by Barrage and colleagues in 2015, where they actually alternate between continuous optimization and the Bayesian sampling approach. So what we are going to do is to build a stability map, which will help us to predict how much the structure will deform depending on the hanging direction. So this stability will be measured by looking at the difference between what we call the suspension polygon. So this is the polygon, the convex polygon that will contain or enclose all the suspension points on the structure, so the topmost points on the structure, and the projected convex hull of the 3D model onto the plane of the suspension polygon. So the closer these polygons are, the more stable the shape will be. So this is inspired by the work of Fu and colleagues. So we built this map by sampling the directions, by using different directions sampled on the Gaussian sphere. And then we explore the hot spot of this map. So these structures here correspond to these different areas. So what we do for this for exploration is that we start with the more stable direction. We run the continuous optimization, and during the process we save all the visited directions. Then we feed a normal distribution to these directions and use this normal distribution to update the stability map. So we decrease the stability for points that have already been visited to avoid visiting them twice. And then we pick the best result. So here are some results. So this the target shape is in green here. The blue shape corresponds to the non-optimized deform shape. And this is what we obtained. So what I forgot to say is that actually the external supports that we use are automatically computed. So the location is automatically computed. And to do that, we first run the optimization the first time. And based on the deformation error, we add these structures. So this is the chair that uses 4 planar supports. This is the table model, and here is our plaster cast prototype. So this one required 1 planar surface, and this is the final structure. This is a star model that required 4 cables. So this is fabricated results, and here are some additional results. So the fertility model requiring 2 cables, and 2 strings and 1 planar support, and a duck with 1 cable and a string. Okay. So all the models that I've shown you so far are correspond to volumetric objects in the sense that they enclose. They correspond to shapes that enclose a finite volume. So to broaden a bit or to show you what we could do with inflatable structures, I wanted to finish with this last project, which is a collaboration with Hiroji's group at MIT Tangible Media Group. And what we wanted to do here was to actually use pairs of panels, so identical panels that would bend to create 3D surfaces. So this is very nice, the fabrication process, because as the panels are identical and superimposed, sealing the structures is very easy. And we can actually use seals of having a specific pattern that allows the material to bend. So for that, we use sealed areas that have a diamond shape. What is interesting is that if you change the height of this diamond, you can actually change the bending angle of the hinges. So the larger the height of the diamond is, the smaller the angle, the bending angle is. So how does this work? So let's use this simple two-chamber structure. So this is what you see from the top. What happens is that if you look at, so let's forget for the inner part for a minute. So let's assume there is no material here, so no fabric here. So if you inflate this structure, its silhouette won't shrink uniformly. This is because if you look at some lines on top of the surface, some lines will curve more than others. For example, the green line here will have almost a circular shape when the structure is inflated, whereas the orange line will hardly curve, and this is because it's closer from the boundary of the structure. So now, if the green line or the projection on the mid-surface of the structure is smaller than the one of the orange line relatively, this means that the distance between the point P and Q here gets larger. So D is larger than W. Now, we do have fabric there. And if the fabric is inextensible, we cannot have distance D, which is larger than W. So what will happen is that these chambers on either side of this red line will rotate around this red line. So this won't change the shape of the panels, but it will decrease this distance D. And since the fabric also resists bending, this distance D won't be smaller than W. Otherwise, you will have extra bending forces. So this means that this distance D is exactly equal to W. So we can actually derive an analytical formula for the bending hinges. So this means that if you have a structure made of a set of chambers like this, you can actually compute the 3D shape using by inflating the different chambers independently and then estimating the bending angles at the hinges. So this is a small video that shows you this mechanism in action. So we use that in a design tool that will ease the design of these structures. So in the tool, you can import polygonal mesh, so not necessarily made of triangular faces. This can be arbitrary polygons. And we create automatically a diamond hinge for each internal edge of the polygon. And the user can change the parameters of this hinge, so the weight and the width and the height of the diamond, and it can launch the simulation and adjust the parameters and have a preview of her structure. So regarding fabrication, we mounted a custom heat sealing head on a standard CNC machine. And we had a modular system where we could actually replace the heat sealing head by another head with a knife so that we could also automatically cut the outer layer of the structure. And one interesting thing to note is that when the heat sealing head gets in contact with the fabric, it actually applies forces on it. And this will create a small depression on the top layer of the structure. And this asymmetry will actually make the hinge bend in the preferred direction. So this is useful because this means that we can actually approximate surfaces that have convex and concave edges by, for example, printing all the seal areas corresponding to the convex edges first. Then we flip the structure and seal the edges corresponding to the concave edges next. So here are some results. So we have all kinds of strips that can curl or zigzag or twist. We have also all kinds of polyhedral structures, closed strips and more complex structures. This is a video showing side by side what we have in simulation and in fabrication. This is unfolding or unpacking structure. This is another example. This is an example of structure used for packaging application. So this is nice because we can create structures that really warp around the objects. Another interesting thing is that we can actually stack multiple layers. So add more than 2 panels for the structure to create different multiple network of chambers that are actuated independently. So we can program different shapes in the same structure. And this is an application where we used the structure on the left, which has this S shape, to program 2 shapes. So this structure can be used, for example, as packaging for a light bulb, and then turns into a lampshade. Okay, so to conclude, I presented you tools for computer-assisted design of inflatable structures, which are based on efficient simulation methods and physics-driven optimization. And I showed you a few applications. So there are still a lot of things to do. For example, in the first project, I told you that we could predict the location of the wrinkles, but we don't do anything to prevent them. So for example, in this fox head example, so the picture is a bit small here, but there are clearly wrinkles forming in the ear that are not desirable. So we could try to avoid them in the simulation, in the optimization. In the second project, I showed you a tool to help the design of inflatable sheets, but we didn't really tackle the inverse problem. So this would be really nice to have. It would also be interesting to consider a denser set of chambers. Also, since you can actually program multiple states, it would be very interesting to look into dynamic systems. So I think this would be super useful for in soft robotics, for example, to get moving robots. And this raises a lot of interesting questions. How many layers do you need? What are the different networks for the chambers that you need to have? In which order? Or what is the timing to inflate them? And how do you transition from one shape to the other one? And we could also consider other materials, especially to have like a smoother transformation from one shape to the other. So this could be done using extensible fabrics or silicone. So there was this very interesting work by Emmanuel Sieffert and colleague, which had with this baromorph. So they used silicone here. And I'm sure there are other things to do. So that's it from my side. Thanks a lot for having attended this talk. And if you have any questions, I'd be happy to answer. Thanks.
Thank you. Thank you very much, Mélina. You can stop sharing your screen now as we move to our Q&A. And we'll let you take a bit of a break and start with a question for Sarah. So when you were discussing the bending versus not bending energy, you showed a picture that had like a fan disc, the typical fan disc shape, and the bunny, and the rods from the fan disc were kind of going through the bunny. I don't know if they were through the bunny or they were like the rods started at the bunny and it went to the, and is that something that happens with your algorithm? Can the rods go from one object to another or go through another object?
Yeah, so in that example, the rods were not going through the bunny. They were attached to each object until one of the rods hit the support surface. That's because we get rid of edges in our graph that intersect objects. But in terms of whether that could exist if I was 3D printing it, that would be okay if they intersect, but if I was assembling it with wooden rods, that would be much harder to do.
Right, I guess that makes sense. Yeah, you can't. You would need to do just one 3D print, right? You can't just 3D. Okay. So our next question for Mélina is, so you showed this optimization of the panels where they were like changing shape to sort of optimize the energy. Do they ever self-overlap when you're doing that optimization?
They don't, but this is not prevented. So in theory, it would be possible. So we don't do anything to avoid this. That's true that in theory, this might happen.
Okay.
Yeah.
So you just haven't seen it in practice.
Exactly. Yes.
Interesting. Our next question for Sarah: have you considered curved rods? Would that help to find a more invisible solution?
That's an interesting question. During this part of the paper, I didn't consider curved rods because all of the previous ground structure methods use straight truss elements, but for my current project, we're actually looking into this. And yeah, it would be sometimes easier to find an invisible solution if they could curve. So yeah, that's a good question.
Okay. Now our next question for Mélina is, many of us are looking at your work from a very geometric perspective. So we wonder if the optimized solution that you solve satisfies some minimum curvature or some like geometric property like that, or like minimizing distortion in the parameterization or something.
That's hard to say. So there are some. So somehow the physics, like the energy density of the material, measures distortion, right? So there is this connection to like change in first fundamental form. So yeah, it tries to minimize this stretching energy, but you really need to account for the material parameters here. And I think the role of the external forces, this also has an important role. So for the inflatables, one thing, for example, is that you couldn't say, like you are looking for an isometry of the panels. For example, if you have a cylinder, this would be the optimal result, right? You want a cylinder, you use like one rectangular panel that is closed on both sides, and then two discs. So this looks perfect. But because of pressure forces, the caps will actually change their shape so as to maximize the volume inside the object.
Okay, that makes sense. Thank you very much. Our next question is for Sarah. So you kind of mentioned at the end that you don't look at the shadow of the rods, and I was wondering, you also don't look at the shadow of the objects, right? Because most of the real world examples that you showed use this sort of like ambient room lighting. But if you had a point light, you could do it so that the shadow of the object falls on the rod, and even if it is like visible theoretically with your energy, it would not be visible because the shadow of the object occludes it. So I was wondering, would that be like a simple thing to add to account for the lighting, or?
That's a good question too. I think, like I said in the end, to account for the rod shadows on their own, when we shoot rays from the viewpoint to the rod, like in traditional ray tracing, if you let that ray bounce until it hits the light for a few passes, then we could incorporate this like shadow into the visibility term itself. But your question about whether it could be hidden on the object's shadow is a good one, because I hadn't thought of that. I'm not sure. I think the answer would be something similar to this. We would have to compute bounces to the light to find out which points in the scene are occluded by that shadow. I don't think it would be too difficult to implement, but it would definitely include more time to compute the visibility term. Yeah.
Okay. Right. So it'd be like a change in the way you compute visibility, I guess, further up.
Yeah. It might be nice to pre-compute where the shadows would be based on a point light, and then add that to the visibility term separately. Yeah.
Right. That makes sense, I think. Okay. So question for Mélina, and you kind of you half answered this in the last 5 minutes. I still wrote this question before that, but I'll try and make it interesting anyway. So we've had a lot of talks about fabrication in this season of the colloquium. So we heard from Dr. Elisa Ross and from Professor Alexander Ion. And Alexander Ion works on like metamaterials that sort of change behavior by changing the shape of the components of the material. And I was thinking, if you could have if you could have many different activations of your like inflatable shape by changing properties, not of like seams being activated or not, but of the material itself.
So you want to change the material properties of
right.
the
So if
structure.
I have like a material that has like a very preferred alignment in one direction, and I like turn it to be preferred aligned in the opposite direction, then suddenly all of the seams would go the opposite way or something like that.
So do you want to have different shapes using different materials?
Right.
Is that you? Right. But in with the same structure.
Yes.
I think there are very like interesting work looking, for example, at. I mean, I'm not sure for the structures I mentioned, I showed today, but you can have structures that have actually which can take different or reach different local minima in the energy landscape. So I guess that if you have more integrated structure, they could actually reach these different local minima, maybe. But for sure, like playing with the material properties will impact the shapes that you get.
That's great. I guess that's like maybe the only case where in an optimization we want to get local minima.
Yes.
Yeah. Okay, so we'll end with a question for you both. Both of you work on fabrication projects where the fabrication step is like a very integral part of the project. And I think about that often because I've been working from home for over a year now, and I haven't seen a 3D printer or like a concrete machine or plaster machine or anything like that in more than a year. So I wonder if each of you could talk about a bit about the challenges that you faced during this year of working in fabrication but remotely, and how you've managed, I guess. So let's start with Sarah.
Okay, yeah, this was a big challenge at the beginning of quarantine. Yeah, nobody was allowed to go to the lab for a while. So when I first worked on this paper, we only had digital results to show. And then as time went on, I think last October, I finally got permission to go into the lab alone and use the printers. And that was nice, but weird to work completely alone in a lab where usually there are a lot of people. And yeah, so it was kind of sad. So I stopped going in, and now I have a smaller 3D printer on my desk right here that's been useful as well. But yeah, I'm kind of hoping to use the hardware room in the lab again soon. That would be nice.
Thank you. Dr. Skouras?
Yeah, for me, it's like, I would say it didn't change much, but for the students I work with, this was a different story. So I have one student who did what Sarah just said. He just took it. So he's like working on a project where he 3D prints curves on a stretched fabric, and he just brought the printer at his place. Otherwise, I would say there are still like a lot of theoretical questions in this project, or things that you can do in simulation. So if you trust your simulator, then you won't get bored for sure. At some point, you do need to compare what you get with the actual results and fit, for example, material properties, but you still have a lot to do. But yeah, being able to access the workshops, like, yeah, it's great, right? Or would be great.
So I guess the answer is trust your simulation software, or write better simulation software.
Yeah, or focus on the parts that don't require so much 3D printing or laser cutting.
Right. That makes sense. All right. So before we wrap up today, let's thank our speakers again for their time, as well as Brandon Blomer, the artist behind this week's poster. And I'd like to end this colloquium season finale by thanking all of our speakers this season, and as well as all of the artists that have designed this season's posters, as well as my co-hosts, Derek Liu and Eric Zhang and Sanbei Ban. Stay tuned for what's next, and have a great day, everyone.
Thank you.